Greetings, everyone. Today we're going to explore graphing rational equations. Now, you want to make sure to have the foldable for this. We have a note sheet to follow along, and it'll be very helpful as we do need the graphs. All right, before we begin, in our foldable, we actually have a few definitions we want to make sure we clarify. The first one is an asymptote. Now, we haven't used this vocabulary word this year, but an asymptote is a line that a graph can get very close to, but doesn't cross. So we'll get more into it with exponential functions, and you might remember this from Algebra 1. But an exponential function just cruises along an asymptote, meaning think of it like a wall. It doesn't cross the wall, but it can go right along the wall. The second thing we're going to experience and use is what's called a hole. Now on our graph, we're going to have holes, which are discontinuities in the graph. So it's an x value that can't be included. You can think of it like an extraneous solution, right? So to denote that on a graph, instead of just a closed dot that we're used to, we're just going to have an open dot, kind of like our step functions. So we've had open dots with inequalities, so we're going to graph it very similarly. The last two definitions are old news, just making sure that you remember that the degree is the highest exponent present in an expression. And then remembering that the coefficient is the number in front of a variable, and we're also going to use the word leading coefficient, which is the number in front of the highest exponent variable. Now, before we get going, let's just talk about the parent graph, the graph of which all these graphs come from. If I was to make a quick little table, 1 divided by 1 is 1. 1 divided by 2 is a half. 1 divided by a half is 2. And so if I start plugging in positive values, I arrive at this function or this graph that looks like this. If I plug in negative values, -1. If I plug in half, it'd be -2. And I'd sort of arrive at this almost rotation or diagonal reflection of the graph. And so that's our parent graph. Now, how we can change this, how it can look different. We can actually end up with graphs that meet together at a vertical asymptote. We could have graphs that meet together but go downwards. We might actually end up with graphs that have two sort of corner curves, but then some middle behavior, like maybe an S curve or maybe a U curve in the middle. So we might have some with middle behavior. But what I want to stress here is this is the general look of all the functions we're going to do. What you cannot have, and what you already know, is you cannot have a graph that looks like this. Even Algebra 1 can remember that because that would fail the vertical line test, right? It would pass twice. So you cannot have a graph where one is above the other. It's not a function. Now, this note sheet that you have, this is just a made-up acronym that helps this process. It makes it so much easier to graph the details without needing a table. So if we can avoid a table, perfect. This will make it so much faster. My suggestion would be to start working on memorizing these topics, and specifically end behavior. You're going to have a lot of information that you're really going to have to memorize. So for the first example, I'm going to go through each piece of the acronym individually, and then we'll tie it all together in the end. So S stands for simplify, meaning let's just simplify our rational function as we have been doing already. If I can factor it, great. If I can cancel, great. GCF. And if you can't simplify anything, I still ask that you write the function because I don't want you to leave it blank, for example, on an assessment. Next, let's talk about holes. Holes occur if a factor cancels. Well, nothing canceled, so we need to write something, so we're going to write none. As a quick little side note, don't write this down, but let's say you factored a function and you arrived at something like this, right? If something cancels, it matters. It was part of the original. And so this is where the whole would come from, the piece that cancels, okay? But we don't have that on this example, so let's move on. Let's take a look at roots. Now, roots, if you would go to your notes sheet, roots also include or are synonyms of x-intercepts. We can also refer to them as solutions. Right? We've found x-intercepts before. So to find your x-intercepts, well, think about it. If I want to know the x, I plug 0 in for y every time. So let's do that. We're going to set the function equal to 0. But what's going to happen every time, and where this rule comes into play, this side note here, if I'm going to solve that, I'm going to multiply this denominator to the other side. So what's it going to become every time? 0. Because it's going to become 0 every time, you can shortcut it and just set the numerator equal to 0. That's why we say that. It's just a shortcut. And then solve. So we're going to subtract 5, divide by 2, so I'm going to have negative 5 halves, but it's a point. It's an x-intercept. So do not write it as x equals. You write it as a point. Let's talk about the asymptotes, vertical asymptotes, meaning what can x never be? Maybe that's the question we want to add in. What can x never be? Meaning what would make my denominator 0? And in this case, x cannot equal 1, right? If I got a 1, I would have an undefined function. So our vertical asymptote, it's a line, so we leave it written as the equation of a line is x equals 1. Togetherness and tangency. All right, the best way to memorize this for T, you'll notice alphabetical. TA over TO, all right? We put it over as a trick to remember. Tangency deals with the numerator. That's why it's on top. And togetherness deals with the denominator. That's why it's on bottom. What this means is if you have the same factor on top, then that means it is tangent to that point. What does tangent look like? Tangent means it touches and bounces off. That's what tangency means. You're going back to geometry here. You dealt with tangency in geometry. Togetherness. What does togetherness mean? Togetherness looks like a graph where the graph comes together. See how I like to joke and say two star-crossed lovers come together at the wall, but they cannot cross. So togetherness means they almost come together. Now, multiplicity means it's the same thing. For example, don't write this down. If I had x minus 2 over x minus 2 over x plus 3, we have the same factor twice. That's tangency. If I flip it around, this is the same factor twice on the bottom. That would mean togetherness. Now, on this particular example, nothing is doubled. There's no multiplicity. So next to t squared, we would just say none. You have to write something. So we're going to say none or no tangency, no togetherness. End behavior, again, please put a star by this one. This is where you're going to have to memorize these 3 rules. All right. First thing we need to acknowledge, what is the degree of the numerator and the degree of the denominator? I like to make a little note. The degree of the numerator is 1 because I have a variable with an exponent of 1. The degree of the denominator is 1 because I have x to the first. If they are equal, then you take the ratio of the leading coefficients. The leading coefficients are a 2 and a 1. 2 over 1 is 2. My end behavior is set by the horizontal asymptote of y equals 2. Again, if the degrees are the same, you take the numbers in the front. You're going to have to work on that. That's going to take some time. Crosses. Crosses uses the previous information. So here's what I do. I go write down whatever I got for the previous answer. 2. And you're going to set it equal to your simplified function. Solve it. All right, let's put the 2 over 1. Let's cross multiply. I'm going to have a 2x minus 2 if I distribute, and a 2x plus 5. Look what happens if I solve this. My variables go away and I'm left with negative 2 equals 5. Does negative 2 equals 5? No. So if it's a not true situation, then we say no crossing. It doesn't cross, however you want to write that. Y-intercept, this is algebra 1 stuff, right? If I want to find the y-intercept, I plug 0 in for x and find my y number. So this is really quick. 0 plus 5 over 0 negative 1. So if I plug in 0, I'm going to arrive at negative 5. All right. This is a combination of all the information. Let's begin to graph. The first thing you want to do is graph any dots that you have. I have negative 2.5 comma 0, and I have 0 negative 5. Next, we want to graph our asymptotes. I have the asymptote at x equals 1. Now we show this with a dashed line. It slices the x at 1. And then we also have a horizontal asymptote, which determines our end behavior, at y equals 2. That's a horizontal line. It slices the y at 2. Now, I'm not going to cross the horizontal asymptote. There's no togetherness, no tangency. Now think of that parent function. Remember how we graphed this? Can I make any assumptions here? Yes. I have 2 dots, 2 green dots, which means I'm going to fill this corner. I can make that assumption. Now, if there's no togetherness, then my other piece has to be over here. They can't come together. So first of all, I can't exist there because that would be not a function, right? And I can't exist here because there's no togetherness. So that's my only other option. Now let's say you don't like that. You're like, I feel like I'm guessing. I don't like guessing. Then make a quick little table. If you plug in, let's say 3. Well, 2 times 3 is 6. 6 plus 5 is 11. 3 minus 1 is 2, so this would be the same as 5.5 at 3. 1, 2, 3. I exist at 5.5. 1, 2, 3, 4, 5.5. Was I pretty close? Yeah. And I don't need you to be exact. I care about, do you understand the general shape? Let's talk about domain. I start existing at negative infinity all the way to 1. Parenthesis. I don't exist on the asymptote. I pick back up after the asymptote and I go to forever. Range, I start at negative infinity. I exist all the way to the horizontal asymptote. I don't exist at it, so I pick back up after it. All right, let's try this process again with this problem, but I'm going to take care of it all on one slide. So, simplify. S. The only thing I can do to make it a little easier is to write that denominator twice. Makes it easier to look at. Holes. Did anything cancel? No. No holes, none, NA, whatever you want to write there. But we have to write something. R, roots. Roots mean, a little side note, right? Roots exist, meaning find your x number when y is 0. If I set my function equal to 0, I'm going to multiply that denominator over, which gets rid of it. Wait a second, can 0 equal 4? No. So there are none. I can't solve anything, so there are no x-intercepts. Interesting. Asymptotes. Asymptotes are where x cannot exist. Look at that denominator. What would make that denominator 0? A 1. I'm going to color code this actually. X equals 1 is my vertical asymptote. It's where I cannot exist because it would make my function undefined. So let's graph that right away. Tangency and togetherness. Okay, alphabetical. Do I have the same thing on top? None. Nope. Do I have the same thing on bottom? I do. See how I have that same factor twice? So the way we identify this is we say together at x equals 1, right? Because that's the factor I have twice. That's the solution I have twice. That's what togetherness looks like algebraically. Okay. Now, I can't graph it yet, so I'll come back to that. End behavior. End behavior, we care about the degree of the numerator and the degree of the denominator. The degree of my numerator is 0. It doesn't have a degree because there's no variable. Okay. The degree of my denominator, though, is 2, meaning if I multiplied that out, I would have a quadratic function. So I would say x squared, right? So we call this bottom heavy. If it's bottom heavy, look at your notes sheet. That means your horizontal asymptote that creates your end behavior is y equals 0 every time. You guys, this makes sense. Look, we said we don't cross the x-axis. We said because there's a horizontal asymptote. R and E go together in this case. No x-intercepts because there's an asymptote there. Crosses. Crosses means you take the answer from E and you set it equal to your function. Well, guys, we already proved this. If I multiply that over, does 0 equal 4? No, so there's no crosses. Your y-intercept is found by plugging in 0 for x and finding your y. If I plug in 0 for x, I'm going to have, let's see, -1. -1 squared is 1. 4 divided by 1 is 4. So I exist at 0, 4. All right, I went through all the rules. Can I make any assumptions about curves? Sure can. Look at that big white intercept. That means I exist in this little corner. You can make that assumption based on the parent graph. Now, here's where the togetherness comes in. First of all, can't exist here. That's not a function, right? I have togetherness, which means the two star-crossed lovers come together at the wall, but they cannot meet or cross. That's what togetherness looks like. So, therefore, I don't exist here because I have togetherness. Let's talk about the domain and range. Domain and range is going to look different. First of all, domain, forever left all the way to the wall at 1, and then I pick up on the other side of the wall, and I go to infinity. Now, your range is different. My range begins at 0 and goes to infinity. I only exist in the top half of this graph. It must be a parenthesis because it's an asymptote. I can't exist exactly at 0. All right, let's try another one. Simplify. I can factor that numerator. I have a -2 and a +1 over a -2. Oh, this cancels. I'm left with x plus 1. Hold up. You guys, we're left with a line. We're left with a line. I'm going to do a quick little sketch. Cross at 1, slope of 1. I'm going to have a line like this kind of, right? But let's do a little bit more information. Holes, we had something cancel. X minus 2 cancels, right? If I solve my cancellation, I get x equals 2. Well, a hole is a dot. So when x is 2, what's y? Just plug it in. If I plug it in, 2 plus 1 is 3. I have a hole at 2, 3. Put a big open circle there. Roots, I can find my roots, right? Roots are saying, hey, when y is 0, what's your x? Well, let's see if I set my function equal to 0, my simplified function, right? I arrive at -1. So let's go plot that dot. -1, 0, that makes sense. Yep. And here's the thing, you guys, this is a line. I do not care about asymptotes. It's not rational, or togetherness or tangency. I don't care about horizontal asymptotes or where it crosses the asymptotes I'm not even talking about. So if it's a linear function, you don't need all this SHRATTECY stuff. Let's go down to y-intercept though. I already know it's going to be 0, 1, but you could plug it in if you want to make sure. Right? That makes sense. I'm crossing at 1. That's my y-intercept. So all I have is a regular old line with a slope of 1 that happens to have a hole in the middle. Domain. My linear function exists up to that x hole. It continues on the other side of the hole to infinity. Similarly, the y exists all the way to the y value of the hole and then picks back up afterwards. So you will encounter this on your homework. If it simplifies to a linear, graph the line, think about the holes, the roots, and the y-intercept. I know one more. I know this is a long one. Bear with me. I'm trying to show you an example of each type that you're going to encounter that have horizontal asymptotes. Step 1, simplify. I can't simplify the numerator, but I can factor the denominator. Holes, did anything cancel? No. Roots, if I set the numerator equal to 0 and I solve, I would subtract 5, I would divide by 2, I would square root. Oh man, let's take a look at that. Okay, so x equals, I'm going to have an I and a plus or minus because it's a negative and it's a radical. And I have to rationalize. I have to multiply top and bottom by 2. So I'm going to have radical 10 over 2. Now, can I graph that? No. It's similar to parabolas. We have a solution that we need to show. It's just not physically on the graph, which is a hint. I have no physical x-intercepts, all right? All right, asymptotes. Where would x make my function undefined? X equals 5 and negative 5. Do you see where that came from? Look at that denominator. Wait a second. I'm going to have 1, 2, 3, 4, 5. A vertical asymptote here at negative 5 and a vertical asymptote at positive 5. 2 of them. This is new. Tangency or togetherness. Do I have the same factor on top? None. Do I have the same factor on bottom? Nope. No tangency, no togetherness. End behavior. The degree of my numerator is 2. The degree of my denominator is 2, right? Highest degree. If the degree is equal, then I care about the ratio of the leading coefficients. 2 over 1 creates a horizontal asymptote at 2. Okay, we take the leading coefficients if the degree is the same. That would be a really good note card study tip, right? Like I could write those rules on a note card and know and work on memorizing them. Crosses. Crosses, you take the previous answer and you set it equal to your function. Let's put that 2 over 1. If I cross multiply, I'm going to have a 2x squared minus 50. See how I distributed the 2? And the 2x squared plus 5. If I go to solve, look what happens to my 2x squareds. They go away. Does negative 50 equal 5? Nope. So there's no crosses. Y-intercept, plug in 0 for x and solve. We would arrive at negative 1/5. So I have a dot at 0, negative 1/5. You guys, that's the only dot I have. That's the only dot I have. Okay. I'm going to need some table work here. Like I can't make any assumptions. So to start off, I'm going to do a little bit of a table off to the left here. I'm going to start by plugging in -6. I need some kind of information. I'm going to plug in -2. I'm going to plug in 2, and I'm going to plug in 6. If I plug in -6 into the function, right, use your calculator. I'm just going to talk it out. -6 squared is 36. 36 doubled is 72. 72 plus 5 is 77. Plug it into the denominator. -6 squared is 36. 36 minus 25 is 11. I've got 7. Let's go plot that dot. At -6, I exist at 7. Perfect. That's enough information to know that I curve here. Let's jump down to 6. Wait a second. If I'm squaring a negative or a positive, I'm going to get the same answer. Plug it in, but we get 6 and 7 again, which means I exist in this little corner. All right, let's talk about the middle. I do not cross the horizontal asymptote. Let's talk about that. That means I can't be an S-curve. See how that crosses my orange line? That means I can't do this. That means I have to exist in the bottom somewhere. I have to exist down here, which means my only option is going to be a U shape. So let's confirm that. If I plug in +2, 2 squared 4, 4 times 2, 8, 8 plus 5, 13. 2 squared 4 minus 25, negative 21. So that would be just over -1/2. At 2, I'm just over -1/2. Well, guess what? If I plug in -2, I've got the same thing. I have a parabola, a U, that's going to approach the wall and approach the wall. If you don't like assuming that, plot a few more dots and see what happens. So let's talk about the domain. This one has a weird domain. Excuse me, weird range. Let's talk about the domain. Domain, -infinity to the vertical asymptote of -5. I pick back up at -5, and I go to +5. And then I pick back up at +5, and I go to infinity. I have 3 domains because I have 3 pieces to my graph. Range, though, here's where I'm a little bit open to this. All right. I'm going to do the top half first. I exist from 2 to infinity, right? That's those 2 top pieces. But the bottom piece, I exist from -infinity. Now, if I was going to be exact, and I'm for sure about my parabola, I could put my y value of -1/5. Now, if you're not making a table and you're making some assumptions, you guys, I would be okay if you said -infinity to 0, because I see I'm going to 0, but I have no x-intercept. Or to be totally honest, I'd be okay if you said 2, right? Because that's my horizontal asymptote. Now, specifically, I think 0 would be good since you had no roots. If you want to be exact, I would do the -1/5. I'm going to be a little bit open because I don't have the expectation of you using a graphing calculator, and I don't have the expectation that you're using this really detailed table. Okay? Oh my goodness, that was a lot. I know. Thanks for bearing with me on this. This is a tough lesson. Maybe break it up. Maybe rewatch the tougher examples. Check out Google Classroom to see what the task is. Make sure if you are behind a little bit, we have a second video. That second video is going to talk about what happens if I'm top heavy. We didn't do an example like that. If we're top heavy, that means we have what's called a slant asymptote, and that's a whole nother video. Okay, so if you're behind a little bit, you might have 2 videos to watch. Take a look. Let me know what your questions are. It's going to take time. We're going to spend a lot of time on this. So bear with me. Good job. And until next time, have a good one.